Welcome to the fascinating world of parasite population dynamics. Imagine you are a detective trying to predict how a criminal gang will spread across a city. In parasitology, we do exactly the same thing, but our criminals are parasites, and the city is a host's body, or an entire population of hosts. By understanding these mathematical dynamics, we can predict disease outbreaks and figure out the exact best ways to stop them. Let us dive in.
To begin our investigation, we desperately need a way to measure the exact spreading power of a parasite. We need to know if a single infected host will spark a massive outbreak, or if the infection will just fizzle out harmlessly. This brings us to the most famous and important number in all of infectious disease biology, the basic reproductive number, denoted as R0. It is defined as the average number of secondary infections produced by one single infected individual when introduced into a completely susceptible population. For microparasites, like malaria, it is new hosts infected. For macroparasites, like tapeworms, it is surviving female offspring. This concept is incredibly important because it serves as the ultimate threshold for public health worldwide.
Now that we understand what R0 represents, let us look at how it dictates the fate of a disease. If the value of R0 is strictly greater than 1, the parasite population will grow, inevitably leading to an epidemic. Each infected person infects more than one other person, so the numbers snowball. If the value is exactly 1, the disease becomes endemic, meaning it stays at a stable, constant level in the population, without growing or shrinking. Finally, if we can use medicines, vaccines, or bed nets to push R0 below 1, the parasite will eventually go extinct because it cannot replace itself fast enough. This is the primary goal of all parasitology control programs. This conceptual threshold leads us directly to its mathematical formula. The basic reproductive number, R0, is calculated by multiplying 3 key variables. First, beta represents the transmission probability, which is the biological chance that a contact results in an actual infection. Second, C represents the contact rate, or how many susceptible hosts the infected individual interacts with per day. Finally, D represents the duration of the infection, meaning how many days the host remains infectious and capable of spreading the parasite. If any of these 3 variables increases, the total number of secondary infections will also increase, making the outbreak worse. Lowering any of these factors is how we stop an epidemic. Before we move on, let us see this formula in action with a concrete example. Suppose a dog is infected with a newly discovered strain of intestinal hookworm. We are given a transmission probability of 0.2, a contact rate of 5 susceptible dogs per week, and an infection duration of exactly 4 weeks. We need to find the basic reproductive number to understand the threat level. We simply multiply the transmission probability, the contact rate, and the duration together. Multiplying 0.2 by 5 gives us exactly 1 new infection generated per week. Multiplying this by the 4-week duration gives a final answer of 4. This means 1 infected dog will pass the hookworm to 4 healthy dogs. Since 4 is greater than 1, a severe outbreak is imminent. Now that we have seen an epidemic scenario, let us calculate what happens when we intervene. Local veterinarians introduce a powerful deworming medication that reduces the duration of the infection from 4 weeks down to just 0.5 weeks. We keep the transmission probability and contact rate completely constant. By substituting the new, much shorter duration into our equation, we still get a rate of 1 infection per week, but the parasite now has much less time to spread. Multiplying 1 by 0.5 gives a new basic reproductive number of 0.5. Because this value is strictly less than 1, the infected dog will not even replace itself. The medication has successfully broken the chain of transmission, and the parasite population will eventually die out completely. This mathematical result is perfectly captured in this visual diagram. At the top, we see the epidemic scenario, where R0 is greater than 1. A single infected host, shown in red, successfully transmits the parasite to multiple secondary hosts, shown in blue. The arrows represent the chain of transmission, branching out and multiplying. At the bottom, we see the eradication scenario, where R0 is less than 1. The infected host is treated, and the transmission chain is broken, represented by the red X over the secondary infection. Lowering transmission probability, contact rate, or infection duration is the primary goal of all parasitology control programs. Understanding this single number is the key to mastering epidemiology. Having explored how parasites spread between hosts, let us now zoom in and look at what happens inside a single host's body. Imagine a few parasitic bacteria entering your stomach. At first, they have unlimited nutrients and plenty of space, so they multiply incredibly fast. However, they cannot keep multiplying forever, or the host would literally explode. Eventually, they run out of food, or your immune system starts fighting back, forcing their growth to slow down and stabilize. This realistic pattern of multiplication is called logistic population growth. It describes a situation where a population initially grows exponentially, but then the growth rate decreases as the population size approaches a maximum limit. This maximum limit is known scientifically as the carrying capacity of the environment. Before we look at the math, we must understand why carrying capacity is so vital. Understanding logistic growth explains why most parasitic infections do not instantly kill their hosts. Parasites have evolved over millions of years to reach a stable population size where they can survive and reproduce without destroying their home too quickly. In parasitology, the carrying capacity represents the absolute maximum number of parasites a specific host can support, based on available nutrients, physical space, and immune pressure. For doctors and veterinarians, knowing the carrying capacity helps them understand when a parasite load has reached a dangerous, life-threatening threshold. This knowledge dictates when immediate surgical or medical intervention is absolutely required to save the host. This biological concept of limited resources is perfectly captured by the logistic growth differential equation. The term dn over dt represents the rate of change of the parasite population over time. The variable n is the current number of parasites, and the variable r is the intrinsic growth rate, which is how fast they reproduce in perfect conditions. The variable k represents the carrying capacity of the host. Notice the term inside the parentheses. When the population n is very small, this term is close to 1, leading to rapid, almost exponential growth. But as n gets closer to the carrying capacity k, the term inside the parentheses approaches 0, which mathematically forces the growth rate to slow down and eventually stop completely. Let us apply this formula to a patient infected with a small population of tapeworms. We are given an intrinsic growth rate of 0.1 per day, a carrying capacity of 100 worms, and a current population of exactly 10 worms. We want to find the current rate of population growth. We carefully substitute these values into our logistic differential equation. Our first mathematical step is to calculate the fraction inside the parentheses, 10 over 100, which simplifies to 0.1. Subtracting this from 1 gives 0.9, which physically represents the remaining available space and resources in the host's body. Multiplying everything together gives a final answer of 0.9 worms per day. Because the population is still far below carrying capacity, growth is relatively fast and unhindered.
Now, let us look at the exact same patient a few months later. The tapeworm population has grown significantly to 95 worms. The intrinsic growth rate and carrying capacity remain exactly the same. We substitute the new population size of 95 into the exact same equation. The fraction inside the parentheses is now 95 over 100, or 0.95. This indicates that 95% of the host's maximum capacity is already filled. Subtracting this large fraction from 1 leaves only 0.05, proving that very little space remains. Multiplying this out gives a new growth rate of 0.475 worms per day. Even though there are many more worms present to reproduce, the severe lack of space and nutrients has cut the actual growth rate in half. The parasites are barely replacing themselves.
This mathematical stabilization is beautifully illustrated by the logistic growth S-curve shown here. On the horizontal axis, we have time, and on the vertical axis, we have the parasite population size. Notice how the blue curve starts with a steep upward slope. This is the rapid exponential growth phase we calculated in our first tapeworm example, where resources are abundant. But as the population climbs higher, the curve begins to bend and flatten out. It approaches the dashed horizontal line, which represents the carrying capacity, K. This delicate biological balance prevents the immediate death of the host, ensuring the parasite's long-term survival. Mastering this concept allows us to understand the chronic nature of many parasitic infections. We have covered a lot of ground today, so let us review our key takeaways. First, we learned that the basic reproductive number, R0, is the ultimate predictor of a parasite's evolutionary success across a population. We must push R0 below 1 to eradicate a disease. Second, we zoomed in to see that inside a single host, parasites follow logistic population growth. They do not grow forever. Instead, they are limited by the host's carrying capacity, which forces the population to stabilize. By understanding both the macro-level spread and the micro-level growth, you now have the mathematical tools to analyze and combat parasitic infections. Great job, and keep exploring the fascinating world of parasitology.